Okay, so this week we're going to go through the beginning parts of Taylor series. So today we're going to go over what a Taylor series is, how to find the Taylor series, and the interval of convergence. Then on Thursday, we're going to do a few more examples and look at some of the applications of Taylor series. Okay, then next week we'll go through the remaining applications of Taylor series. Okay, so remember from last year when we did the linear and quadratic approximations to a function. So if you want the linear approximation, we wrote it as f of x is approximately f of a plus the gradient f prime at a times x minus a. Right, that gave us the tangent line or the linear approximation. Then we also had the quadratic approximation, which was a bit better. And that was taking the linear approximation and adding 1/2 f double prime at a x minus a squared. Okay, that made it a little better of an approximation. Okay, now we can extend this pattern to the nth order approximation. So we can write the nth order approximation to f at x equals a. Okay, so here we're going to have the sum up to n because there's going to be n terms. We can write this as f of x is approximately the sum as n goes from 0 to capital N of the nth derivative at a over n factorial x minus a to the n. Right, we just continue that sum. So we have first order, second order. Here we have nth order. Okay, and it's still an approximation, so we still use that squiggly equal to sign. Now, if we take the limits as this n goes to infinity, the approximation will become exact. So we have f of x is now equal to the limits as n goes to infinity of the sum little n goes from 0 to capital N of the nth derivative at a over n factorial x minus a to the n. Okay, so you have infinitely many terms added up. That will give you the exact function. So the approximation becomes equal to. Okay, so this is called the Taylor series. So the Taylor series of f, and we say that it is centered at x equals a. That's just the wording we use. Now, for a very special case of this, if a is 0, we call it a Maclaurin series. But it's just a special case of a Taylor series. Right, it's just the name that we give to that special case when a is 0. Okay, but for most of the time, I'm just going to refer to it as a Taylor series. Okay, now an important note, not all functions have a Taylor series. So some functions do have a Taylor series and we can calculate it. Other functions do not have a Taylor series and we can't do the calculation. So not all functions have a Taylor series. Okay, so the set of functions that do have a Taylor series, we call those analytic functions. So if it does have a Taylor series, we call it an analytic function. It's just the name given to that group of functions. Okay, so this over here, with this limit of the sum here, we can think of that as like the first principles way of calculating this. So, for the derivatives, we had f of x plus h minus f of x over h, and we took the limits. That was like the first principles definition for the derivative. Then for integrals, we had the limit of the Riemann sum. Right, we had to do that whole long way. For Taylor series, we have a similar thing. So if you want to do it right from the beginning, we have to use this formula. We're going to do it for 3 examples, and then we're never going to do that again. Okay, it's much too difficult. So we'll do it for 3 just to get the idea. After that, there's some tricks that we can use. Okay, so please, stay away from doing it from first principles unless you want some extra practice. But, besides that, we're going to do it a different way. Okay, so put a big box around here. This is the first principles definition that we'll use. Again, only for these 3 examples. After that, we're going to use some other tricks. Okay, so we will find the Taylor series for e to the x, cos x, and sin x using the definition, and then after that we'll do other methods. Okay, so let's have a look at the first one, e to the x. So what do we need? Okay, we need to calculate this right-hand side here. So in particular, we need the nth derivative. So we need the 0th derivative, the first derivative, second, all the way to n. Okay, so let's have a look at that. So the 0th derivative, that's just the function value. So that will be e to the x. Okay, let's say we want this centered at a equals 0. So we can substitute x equals 0 and we get 1. Okay, that will make things just a bit easier for us. Okay, now we need the first derivative. So the first derivative of e to the x is e to the x. Okay, and then at 0, this will just be 1 again. Okay, what about the second derivative? That will still be e to the x, and at 0, that will still be 1. So we see that every derivative evaluated at 0 is just 1. Okay, so what is our Taylor series going to look like? So we're going to have e to the x is equal to the sum. N goes from 0 to infinity. The nth derivative, we saw all of those were 1. So it's just 1 over n factorial. And then we have the x minus a to the n. But a is 0, so this is just x to the n. Okay. And that's our Taylor series for the exponential. Please put a box around that. You will need to know that. Okay. Any questions for this first one? All good. Okay, let's have a look at the second one. So this was number 1. Number 2. Here we have f of x is equal to sin x. And again, centered at a equals 0, just to make things a bit easier. Okay, so what do we need? We need the 0th derivative, the first derivative, second derivative, and so on. So as before, the 0th derivative, that's just the function value, okay, whatever it is. So that's going to be sin x. Okay, and then at 0, sin x is 0, so this just gives 0. Okay, what about the first derivative? So let's take the derivative. So f prime, that's going to be cos x now. And cos at 0, that will be 1. Okay, so we got 0 and we have 1. Let's do the derivative again. So we have f double prime. Now we have to do the derivative of cos, so that's going to be minus sine. Okay, and minus sine at 0, that's just going to be 0. Okay, we'll do this one more time, and then you'll see what the pattern is. So let's look at the third derivative. So now the derivative of sine, that's cosine. We got the minus in front, so that will be minus cosine. Okay, and again, when x is 0, it will be minus cos of 0, so that will just be minus 1. Okay, so what sort of pattern do we see here? We see that the first one is 0, then next is 1, then 0, then minus 1. Any guess what the next one will be? 0. Yeah, so we can see the pattern there. So starting with the 0th derivative, that's 0, then the second is 0, the fourth will be 0, and so on. So all even terms are 0. Okay, what about the odd terms? That will be 1, minus 1, 1, minus 1, 1, minus 1. They alternate. Okay, so it'll be plus 1, minus 1, plus 1, minus 1. Okay. So how do we write this as the Taylor series now? So we're going to have sine of x is equal to the sum, n goes from 0 to infinity, so all of that stays. Now we need this to alternate, so it must go plus 1, minus 1, plus 1, minus 1. So that will be minus 1 to the n. Right, because that will go plus, minus, plus, minus. Okay, what about the denominator for this? So this needs to be n factorial, right, for that denominator. But if we go back here, we see that we're only including the odd terms. So it's n factorial, but only for the odd ones. All of the even ones are 0. So if we want to make this denominator all of the odd factorials, what do we need? Not quite. What is it? Okay. Anyone else want to guess? So we only want the odd ones. No, the bottom part, for the factorial. So we want only the odd factorials. So it won't be n factorial, that includes everything. We want only the odd ones. Yeah, think about it. How do we get all of the odd numbers? So we want 1, 3, 5. We want all of the odd ones at the bottom. Okay, imagine it's your final exam. You need to figure it out. What do we do? So we want 1, 3, 5, 7. We want only the odd ones for that n factorial. Yeah, so when n is 0, that we 1. When n is 1, we want 3. When n is 2, we want 5. Yeah, times 2. And then add 1. Yeah. 2n plus 1. Good. That will give us all of the odd terms. Then we still need x to the n. But again, we're only looking at the odd ones. So we do the same thing, x to the 2n plus 1. Okay, please put a box around that. You'll need to know this one. Okay. So there's only 3 that you need to learn, like off by heart. The other ones are all you have to do the calculation for. Okay, and then example 3 for cos. Very similar to the one for sine. So we're going to have f of x equals cos x, again centered at a equals 0. Okay. Again, you can do this for different values of a, but for these examples, we'll make it easy. Okay, so again, we need the 0th derivative, first derivative, second, and so on. So we'll start with the 0th derivative. That's just the function. So that will be cos. Okay, and at 0, this will just be 1. Okay, now we can do first derivative, second, and so on. So first derivative, the derivative of cos, that's going to be minus sine. And at 0, that will be 0. Okay, what about the second derivative? So f double prime. The derivative of sine is cosine, so we're going to have a minus cosine there. Okay, and again, at 0, that will be minus 1. Okay, we'll do one more, and then you'll see the pattern. So third derivative, the derivative of cos is minus sine, so we just get a sine here. And this at 0, that's just going to be 0. Okay, so we have a similar pattern as before. So now all of the odd ones are 0. So 1 is 0, 3 is 0, and so on. And all of the even ones alternate, plus 1, minus 1, plus 1, minus 1. Yeah, so let's make a note. So again, all of the odd derivatives, those are 0. Yeah, and all of the even ones will alternate 1, minus 1, 1, minus 1. Okay, plus 1, minus 1, and so on. Okay, so let's write out the Taylor series. So we're going to have cos x is equal to the sum, n goes from 0 to infinity. Again, it's alternating, so it will be minus 1 to the n. Now for the bottom, we are only interested in the even terms. So how do we make the bottom even? 2n. Good. Yeah, so that takes care of the bottom. Then we need x to the n, but n must be all of the even ones. So x to the 2n. Okay, and again, please put a box around this one. Okay, so these three you will have to know. Okay, it's quite easy. So here, e to the x is just n factorial at the bottom. That's the only thing you need to remember there. Then sine, you have the odd bottom part and then the odd exponent. And then for cos, it's exactly the same, but with the even. Okay. And again, we know cos is an even function, so the Taylor series is even. Sine is an odd function, so the Taylor series is odd. Okay, so it's very easy to remember what goes where. Okay, so little notes. Cos x is even, so the Taylor series is also even. Okay, and the same thing for sine. Sine is odd, so the Taylor series is also odd. Yeah. So if you know the function is even, then your Taylor series will be even. If you know your function is odd, then your Taylor series will also be odd. All right. Any questions about these three? You're all good. Okay. So these three we've done from the beginning. Okay. Please go through it again at home, just from the beginning, so you can redo it. All of the other examples, we're not going to go from the beginning. We're going to use what we know to find them. Okay, so let's look at example 4. So here we have f of x is equal to e to the minus x squared. Yeah, again with a equals 0. Now here, e to the minus x squared, we're not going to look at the 0th derivative, the first derivative, and so on. You could, but it's a waste of time. Why? Well, we already know the Taylor series for the exponential. The only thing that's different from the exponential and this one is the fact that we have minus x squared in the top. That's the only difference, right? So let's look at the one for the exponential. That's going to be the sum. N goes from 0 to infinity. We all know it now. 1 over n factorial, x to the n. Okay, so we know that. So how do we get from this to the one for e to the minus x squared? What can we do? So we know this one. We want that one at the top. What can we do? Yep. Think about it. We've got e to the x. We want e to the minus x squared. What do we do? Okay. Not quite. Think about it. I'll give you a hint. Composition. That's your hint. Composition. So what can we do? Okay. We're out on the side here. So we've got f of x and g of x. We can do f of g. That gives us a new function. Remember last year, composition of functions gives us another function. And you had to do the whole tutorial with the f of the g, and then you put it inside each other and all that. You forgot. Okay. What can we do? We want to put the one function in the other function. We got one of them. What's the other? What do we put? What do we put where? Oh, no, not quite. What do we take? Yeah. No, not quite. Maybe if I give some bonus marks, you'll think quicker. Okay, composition. We're looking for f and we're looking for g. So that f of g is what we have, or what we want. We want e to the minus x squared. I want f, I want g, so that f of g is e to the minus x squared. Okay, think about it. We need f, we need g. Okay, how about 50% extra for the next quiz, whoever gets it? Extra 50% if you tell me f and g. F is? No, not that one. What is it? Which one is it? F is e to the minus x squared. Okay, that's one of them. And g is? Yes, you got it. Okay, nice. Let me get your sheet number. Well done, extra 50. Yeah, so f will be. Okay, so we want to do the composition. So we're going to write this as e to the minus x squared. Okay, so it will be the exponential is the outside function minus x squared, that's the inside function. So here, this is the outside function, and this is the inside function. Okay, so what we do is we get our Taylor series here, that's the outside part, and inside we put minus x squared. Okay, so we got outside function and our inside function. Does everyone see that? Take your silence as a yes. So here we can just simplify this now. So minus x squared to the n, we can write that as the sum, n goes from 0 to infinity. This minus x squared, we can think of it as a minus 1 times x squared. So we can write it as minus 1 to the n over n factorial. Then the n can jump inside, so it will be x to the 2n. Okay. And quick check. On the left side, that's an even function. And the right-hand side, those exponents are even. So that's right. Okay, so here we have e to the minus x squared. All right. Any questions for this one? They're all good. Okay. Let's have a look at a few more. So this was number 4. Let's look at number 5. So here we have f of x is equal to x cos x cubed. Centered at a equals 0. Okay, so we're going to break it up into what we know and what we don't know. So if we ignore the x and the x cubed, we have cos. We know that one. Okay, so let's write it out. So cos of x just by itself is the sum, n goes from 0 to infinity. We know it's alternating, so it's minus 1 to the n. We know it's even, so the bottom part must be even. And so the exponent for x must also be even. Okay, so we've got cos. What we want is cos of x cubed. So we'll do the same trick as before and replace x with x cubed. So that will be the sum. N goes from 0 to infinity, minus 1 to the n, over 2n factorial, x cubed now, to the 2n. Okay, and like before, the 2n can jump inside there, so it will be x to the 6n. Okay, so this will be the sum. N equals 0 to infinity, minus 1 to the n, 2n factorial, x to the 6n. Okay, that's fine. But we're missing this x here in the front. Okay, so let's multiply both sides by x. So we'll get x cos x cubed is equal to, so we times that side, we can times the other side. So that will be x. The sum, n goes from 0 to infinity, minus 1 to the n, over 2n factorial, x to the 6n. Okay, but this x, that has nothing to do with the sum there, so we can take it inside, and then the x will go with the x to the 6n. So this can jump right inside and multiply onto the x to the 6n, so we'll get x to the 6n plus 1. Okay, so that will be the sum. N goes from 0 to infinity, minus 1 to the n, over 2n factorial. And again, the x multiplies into the x to the 6n, so it will be x to the 6n plus 1. Okay. Any questions for this one? You're all good. Okay. Number 6. There we got f of x is equal to 1 over 1 minus x, centered at a equals 0. Okay, now for this one, we actually don't have to do any work, okay, because this is just the sum of a geometric series. Okay, so we'll show that. So if I have a geometric series with common ratio r, then the sum is just a over 1 minus r. Right? Geometric series. Okay. Now, what we have here is very similar, except a is 1 and r is x. So this will give us 1 over 1 minus x. Okay, for a geometric series. But that's for the sum. We can write it out using that sigma notation. This is just going to be the sum. N goes from 0 to infinity, x to the n. Because the common ratio is just x. Yeah, so we didn't have to do any work. We know the sum of a geometric series, and that is in fact the Taylor series for this function. So 1 over 1 minus x is equal to the sum, n goes from 0 to infinity, of x to the n. So we did this just by noticing that it's a geometric series. For homework, you're going to do it the long way. Okay, so you start off with the 0th derivative, you find the first derivative, second, third, fourth, and then try to get that right-hand side. So homework, do the long way. Yeah, so you have f of 0, f1, f2, f3, and so on. All right. Any questions for this one? You're all good. We've got 2 more. Number 7. Here we have f of x is equal to the natural log of 1 plus x. Again, centered at a equals 0. Okay, so what can we do about this? This one is a bit more complicated than the previous one, but there's a few tricks we can use to make it a bit easier. So the first thing is, we know that the natural log of 1 plus x is the integral of 1 over 1 plus x. So that's the first thing. We know that the natural log of 1 plus x is the integral of 1 over 1 plus x. Now, why do we do that? Well, this 1 over 1 plus x is very, very similar to what we just worked out above for 1 over 1 minus x. So we're going to use that. Okay, so the second thing we know is that 1 over 1 minus x is the sum, n goes from 0 to infinity, of x to the n. Okay, so those are the two things we know. We're going to put that together. Okay, so let's do that. So the natural log of 1 plus x is equal to the integral of 1 over 1 plus x dx. Now, this is not quite the 1 over 1 minus x. Here we have plus x, not minus x, but we can fix that. This is going to be the integral of 1 over 1 minus x. Right, we want it to be a minus, so let's just do that. But then we need to put the other minus to compensate. Okay, so now we do have 1 over 1 minus something, so we can write that as a Taylor series. So this will be the integral of the Taylor series of minus x to the n. Right, so we just replace the 1 over 1 minus something with its Taylor series. Okay, now a little bit of a trick. The sum and the integral, we're going to swap around. So this is going to be equal to the sum. N goes from 0 to infinity, minus 1 to the n, and then the integral of x to the n dx. Okay, so we just did a little swap of the sum and the integral. Now this integral over here is very easy. You just add 1 to the exponent and divide. So finally, we get the sum. N goes from 0 to infinity, minus 1 to the n, divided by the new exponent. So n plus 1, x to the n plus 1. Yeah. And that's it. Okay, so homework, there's 2 things here. So number 1, what happened to the plus c? Okay. So there should be a plus c, it's missing. Why is it missing? Okay, think about that. So an idea is look at the left and the right. What happens when x is 0? What happens to the left-hand side? 0. And on the right-hand side? If x is 0? Yeah, so x is 0, all of that's 0. So what does the c have to be? There you go. Okay, good. Yeah, you did your homework already. Okay, number 2, do this the long way. Same as the other one, the 1 over 1 minus x. Do that the long way as well. Right. Any questions about this one? You're all good. Okay. Then number 8. Okay, we have f of x is arctan x centered with a equals 0. Okay, so this one we're going to do very similar to the previous one. We're going to write it as an integral and then do the Taylor series of the inside parts. So here we know 2 things. Number 1, this arctan we can write as an integral. So that will be the integral of 1 over 1 plus x squared. Okay, so we can write it as an integral. And number 2, that inside part, that also looks familiar, like the previous one. We know that 1 over 1 minus x is equal to the sum. N goes from 0 to infinity, x to the n. Okay. So again, very similar to the previous example. Okay, so let's work it out. So we're going to have tan inverse is equal to the integral of 1 over 1 plus x squared. Okay. Now that function, we want to make it look more like that number 2. So we can write it as minus x squared. So this will be 1 over 1 minus x squared. Okay. Now this looks very similar to what we have there for number 2. But instead of x, we have minus x squared. So we just substitute. So this is going to be the integral, and then here we put the Taylor series. Okay, but instead of x, we put minus x squared to the n. Yeah, and we end up with that. Now, same as before, we're going to swap the integral and the sum. So this is going to be the sum. N goes from 0 to infinity, minus 1 to the n, integral of x to the 2n. Okay, so we just swap the sum and the integral around. Now this integral here, very easy. Add 1 to the exponent and divide. So this will be the sum. N goes from 0 to infinity, minus 1 to the n. So the new exponent will be 2n plus 1. And we'll have x to the 2n plus 1. Yeah, and that's it. Again, we should have had a plus c. What happens to that? Yep. Again, let's look at the left and the right. Arctan at 0 is 0. And over here, if I put x equals 0, that will be 0. So C must be 0. Some cases it might not be 0. So just keep that in mind. Okay. Any questions for this one? You're all good. Okay, some extra homework. Yeah. So here are some functions. Please find the Taylor series. So you can use either from first principles, like we did at the beginning, or you can use some of these tricks that we have here. Yeah. Either way, find the Taylor series. So we have f of x is equal to root x. Okay, with a equals 0. And I'll give you a little hint for this one. Okay, n choose k, you know that's choose function. This is equal to n factorial over k factorial n minus k factorial. Okay. So when you do all of the derivatives, you'll end up with something like that. Number 2, f of x equals sine x over x. Again, with a equals 0. And number 3, f of x equals x times the logarithm of x, with a equals 1. Any questions about the homework problems? You're good. Okay. Again, you can try different ways. You can try, like with the first one and the third one, you could do it from first principles quite easily. Second one, don't do that. Use what we covered today. Yeah, but bonus marks and all of that. For number 3, let's say, if you do it the short way, you get your marks. You do it the long way from first principles, you get your bonus marks. Right? That's always the case. For number 2, don't do it from first principles. Okay. Any questions? No. Okay. So Thursday, we'll go through the interval of convergence, and we'll look at some of the applications for this. Okay, there will be 2 main applications. Evaluating complicated limits, that'll be number 1. And number 2, differential equations using Taylor series. Yeah, we're going to be mixing things. Okay, any questions before we go? You're all good. Okay, see you Thursday.